All right. How exciting. Let's get started. Uh, I suppose you probably want to talk about the exam, which apparently, well, we'll see. I haven't looked at your responses yet, but apparently was a complete uh, shock, perhaps. Um, uh, I think you guys probably are underselling yourselves, hopefully. With this sort of exam, most of the credit goes, of course, for the work. So, um, even if you don't get the right answer, like you can still definitely get an A. Like that's not a problem if you have the work that's there and you're showing your application of the concepts. So, um, I wouldn't necessarily worry unless you've completely gone the wrong direction and somehow you know, did something crazy, but we'll see. So I guess for some of you, it might be kind of like a wake up call, like maybe spend a little bit more time working on the homework problems, making sure you really understand them. Most of the questions that I had written, I think only two of them were kind of tricky. The other four were pretty doable. Um, and so what I tried to do was kind of combine bits of multiple homework questions into one. Like, when I gave you the kinetics problem or one of the kinetics problems, and I had you come up with rate laws and then or mechanisms, rate laws for different mechanisms, and then defend which one do you, would probably be the right one. That's kind of just two homework questions put together. So, hopefully shouldn't have been too bad. So, and then the equilibrium problems should not have been that bad either. They were really pretty straightforward. The solutions ones were tricky. Those ones I intended to be kind of the harder ones. So, with that, the exam key is up. You can have a look. I'll be grading those over the next few days. So you'll get a notification on Canvas when I do so. I'll try and put comments in the comment box so you can see, but definitely check the key out so you can make sure that you understand what's happening in the exam. Um, just so you know, I typically do drop an exam as well and replace it with your final exam score if that helps you. So, all is not lost, even if you completely bombed it. Um, again, just kind of consider it like a rationale to put more effort into studying or something. There are tutoring options available as well. So I would definitely take a look at those. One is through Canvas called Net Tutor, and then I'm pretty sure that the library does offer the tutoring as well. With I think her name is Lauren is the tutor this semester, and she'll be able to help you out. So with that, just keep on going. Don't forget, homework is worth pretty much the same as exams. So you know, even if you do terribly on the exams, you can still get quite a bit of credit in a class just by doing the homework. So um, that would be another suggestion for you guys. So alrighty, so I'll you'll probably have your grades by the end of the weekend. I'll prioritize doing that over grading your homework, and then yeah, we'll go from there. So cool. If there's any questions, of course, throw them out. Potentially I've made an error on the key. Just let me know if something looks really strange. I guess Kevin's really good about doing that anyway, so I'm sure he'll let me know if there's any problems. And then if you want tomorrow, we can go over some of the exam bits if you want. Let me know on Discord if you want to do stuff tomorrow. If you want to go over the exam with me instead of just looking at the key, we can do that tomorrow. I'm cool to do that. Otherwise, we're going to start acid base chemistry. technically acid-base equilibria, although our first couple of sections of this chapter don't really have a lot to do with equilibrium, more just kind of acid-base in general. So we can go and get started. It's a miracle. Okay. So for once I didn't make any mistakes. That's awesome. Good to know. All right. Cool. So let's go ahead and get started. So let's have some definitions. We have a couple of kind of old definitions, which were defined by Arrhenius, same guy who did the activation energy equation. An acid will generate protons in solution. So for example, if you take HCl and put it into water, you get hydrogen ion and chloride ion if you dissolve them in water. We'll just put H2O up here or something to indicate that. And so HCl would be considered an Arrhenius acid because it's breaking apart into hydrogen ions in solution. An Arrhenius base will generate OH minus in solution. And something like that would be if we take sodium hydroxide and also dissolve it, we get sodium and hydroxide ions, and everything's well and good. We've got our base. However, these definitions are kind of trash. They're really limited. We don't ever use them anymore, so ignore them. Forget these. We have a couple more advanced definitions that are a bit more applicable. The big limitation here is that for Arrhenius acids and bases, they are limited to aqueous reactions only. And we're going to see that that is a very narrow definition because a lot of the organic chemistry we'll talk about next semester, if you take that, will be acid-base related, and we very, very rarely use water in organic chemistry. So this is a bad thing. So to have a definition that's limited to aqueous reactions. And so we have a couple other ones. Mostly we're going to focus on this one, which is the Bronsted Lowry definition. And it talks instead about how these acids and bases are reacting together. Instead of focusing on how they dissolve, it focuses on what they do in reactions. So we're going to see that, for example, we can take two gases and react them in an acid-base manner. And so we're going to see that when we look at the Bronsted Lowry definition, we're going to see that acids will donate a proton to another substance in a reaction. And bases, on the other hand, will accept a proton from an acid. And so if we look at this particular reaction, if we think about what NH4Cl is, that's NH4 plus Cl minus. It's an ionic compound. If we think about it, the HCl has given its H plus to the ammonia, and as a result we end up with ammonium, and then the chloride would be left by itself. So we can see here that the acid is going to be our HCl, and our ammonia is going to be a base as a result. So the ammonia is accepting the proton from HCl, forming the ammonium chloride. cool. Let's do some examples here of that. Yeah, let's take this guy. Ignoring the fact that this is technically water and CO2, if we just want to look at this particular one, you kind of want to focus on the anions for this. The sodium is not going to matter at all for this reaction. We can kind of just ignore it. If we look at the anions here, we have acetate. If we look at acetate in the product side, over here, we see that it has lost a hydrogen, which means that this has got to be the acid. It's going to be giving away its hydrogen ion over the course of the reaction. And if we look at the other anion, bicarbonate is becoming carbonic acid, gaining, no, I can spell, gaining, not electrons, protons. So over the course of the reaction, the bicarbonate is going to be gaining a proton, and so we're going to see that the bicarbonate is going to be our base in this reaction. All right, hopefully so far so good. You kind of just want to evaluate your anions and see what's happening to them. And then we're going to have some more terms, but let's do another example. All right, let's go ahead and look at some comparisons here. So let's look at our anions. If we look at the bicarbonate, if we're to try and think, okay, which one of the products is this bicarbonate most similar to, I hope we can identify that that is going to be the product coming from the bicarbonate. And we can see it has lost a hydrogen over the course of the reaction, meaning it is the acid. And let me do this one in green. Remember that water is the same thing as HOH. We can see that this one has gained H+, and as a result, this is going to be our base. All right, so far looks good. We're going to see that these are going to be what are called conjugate pairs. We're going to see that in this reaction, when we have lost our hydrogen on the bicarbonate ion, remember this acted as an acid, we're going to see that this guy is going to be called the conjugate base. Because if we flip our reaction around, although this particular one is unlikely to happen, if we were to flip this reaction around and do it in purple instead, presumably we could get our products out from this reaction. Unlikely, but could happen. Notice this time that the opposite process would happen. So where it had lost a proton in the forward reaction, now if we look at it in reverse, it'll be gaining a proton, which would make it a base. So in an acid-base reaction, we're going to have what are called conjugate pairs, where whatever your acid is in the forward reaction becomes the base in the reverse reaction. So let's indicate that here. So if you were to reverse your reaction, your acid and base would swap. So your acid becomes the base, your base becomes the acid. And then if we look at our base in this example, we had OH minus was our base, becoming H2O. That would be our conjugate acid. So if we're just to label these, that's what we would do. All right, and we would see again here over the course of the reaction this time, we would be losing our hydrogen ion, so we're acting as an acid. So it's going to work in reverse, just like the previous one. If you've noticed, we've had two reactions here that have sodium bicarbonate acting in different ways. Aha, we have a term for this. We would call that amphiprotic or amphoteric. I don't know why we have two words for it, but it's a substance that can act as either an acid or a base. And that would just depend what it's reacting with. So if we react an amphiprotic substance with an acid, it will act as a base. If we react it with a base, it will act as an acid. Some things will fall under this category, some things will not. We're going to see that sodium carbonate, or rather, okay, let's just take a look at this bicarbonate actually. It can either gain or lose protons, right? So it would fall under this category. If we were to look at something like this, there's no way that this can lose hydrogen. It doesn't have any hydrogen. So as a result, carbonate cannot be amphiprotic, but bicarbonate can. So obviously you can't lose hydrogen if you don't have any. So we're going to see that sometimes substances will be amphiprotic or amphoteric. You can use these terms interchangeably. All right. So far, so good. Just definitions here, I suppose. Alrighty. So, in that case, let's go ahead and talk about water. Water is an interesting substance that is amphoteric because what happens with water is it can autoionize, meaning it can transfer a proton to another water molecule. One water molecule can come up and snatch a proton from another one. Because it is amphoteric, it can act as either an acid or a base. We call this, by the way, the autoionization or self-ionization. Water is special in that it does this. Not very many things do. It can form H3O plus and hydroxide if two water molecules were to transfer a proton between them. Often case, by the way, we'll just talk about H plus when we refer to hydronium. So hydronium technically is what's happening in solution. You might even find more complex ions with hydrogen and water, but just for simplicity, we often just refer to this as H plus, just in terms of making things easy for us, not having to write H3O plus every time. We often just write H plus instead. But really, H3O plus is much more close to reality. You don't typically just have protons flying around doing nothing. So really, if we look at that first reaction we did earlier, technically, this should be what we've written. Instead of just writing H plus and Cl minus. This is in reality what's happening, but often we would just write this, just for simplicity. So this is reality here, and this is just the easy way to do it. Okay, so oftentimes we'll see H plus instead of hydronium. Okay, anyways, let's put some state symbols on these. It turns out, as an equilibrium reaction, we can write the equilibrium expression for this. Of course, we ignore liquids. So our equilibrium expression for this would just be hydronium times hydroxide, or as we'll more often do it, hydrogen times hydroxide. At 25 degrees, this number is 1 times 10 to the minus 14. What does that equilibrium constant tell us, by the way? Very small equilibrium constant means that we favor the reactants, right? Absolutely. So we have a ton more water than we would have either of these ions. So these ions don't really make up a very large proportion of your solution in plain water. We don't really see a lot of them. If we go ahead and solve each one of these, since they should be equal to each other, we're going to see in a neutral solution we're going to see that these two would be equal to each other. And so those would be 1 times 10 to the minus 7, each of those. Very, very small concentration. So this is happening, if we have a mole of water, I guess we have 55 moles of water in a liter, but we're going to see that, that's what, 1/10,000,000th of those molecules will be ionized. Not a lot. Actually, I guess 100,000,000th if you think about it, but doesn't matter. Very, very small amount. But it happens. And we're going to see that placing acids and bases in water will alter these numbers. However, the equilibrium is always going to be true. So we're always going to have the Kc for water being 1 times 10 to the minus 14 at 25 degrees Celsius, not negative. And so we're going to be able to calculate the hydrogen ion concentration if we're given the hydroxide concentration, or vice versa. So let's take a look at this. In a solution of, or let's say HCl, or let's make it a little easier, or harder rather. we can see what the hydroxide concentration is going to be. So if we think about this HCl, as we learned last semester, HCl is a strong acid. We'll talk about that in a bit as well. We'll go over that again. But that means it's a strong electrolyte that's going to fully dissociate in solution. So 0.02 molar HCl means the same thing as that many molar of hydrogen ions. So if our equilibrium constant is 10 to the minus 14, we can just plug in our hydrogen ion concentration. And we would calculate our hydroxide concentration to be, let's see, 5 times 10 to the minus, that's going to be minus 13. I really should not do these in my head, although this is not that difficult. Divided by 0.02. Hooray, I did it. Okay. So yes, that would be our hydrogen ion concentration, or hydroxide ion concentration in terms of molarity. All right. Often, instead of Kc, we just call this Kw for water. It's just the Kc for water, self-ionization. All right. So we can do all sorts of fun stuff with that. All right, as you can see though, oftentimes with this acid-base stuff, we're dealing with really, really small numbers, right? 10 to the minus 13, 10 to the minus 7. We're going to see we have a lot of small numbers going on here. And so we have a scale to make things a little bit more manageable for us. And that's going to be the pH scale. pH stands for power of hydrogen. And so we're obviously, since the word power is there, we're talking about exponents, right? Something raised to the power of whatever. We're going to see the pH of a solution is going to be the negative log of your hydrogen ion concentration. So if we were to take that same solution from before, where we had the 0.02 molar hydrogen ion concentration, we can say, okay, the pH would be negative log of 0.02. If we do this, negative log 0.02, we get 1.69897 ... Okay, so we're going to see how to work with this pH scale in a second, but let's think about sig figs for a second here. It's been a long time since we've done logarithms for sig fig purposes. Just so we remember, for sig figs, only the numbers after the decimal can be significant in a logarithm. So, if this number had 2 sig figs, we're going to need our answer to have 2 sig figs, which means we would round this to 1.70, which would have 2 sig figs. We do not count the 1 as part of the sig figs for this, because that 1 actually refers to the exponent component. So we're actually only going to be looking at numbers after the decimal for sig figs with logarithms. Okay, so we vaguely talked about that, I think, last semester, but just a refresher here for logarithms, it's numbers after the decimal only. Okay? Cool. So pH typically will run from 0 to 14, although you can certainly have negative pHs or pHs above 14. Those exist. Wow. The spam has gone through my spam bot. Because they've put a space in there. Obviously, ignore this wanna become famous with 1,000 accent marks. Here, maybe let's see if I can delete this. I don't want to reply to it. I don't know how to delete it right now. I'll deal with it later. Actually, just ignore it. So we're gonna see that everything that's gonna have a pH lower than 7 will be acidic, and everything that has a pH above 7 will be basic or alkaline. They're the same kind of term there. And so, by just looking at the pH of a solution, we can determine whether it's acidic or not. Right at 7, of course, is where we have neutral, but very few solutions are actually neutral. Most of them will be either acidic or basic. And so we're going to see that the closer we go to 0, the smaller our pH is. That's going to mean it's more acidic. Because it's a negative logarithm. So the smaller your pH is, the more acidic your solution is, which means you have the higher concentration of H+. On the other hand, a large pH, which would be something that's more basic, means you have a high concentration of hydroxide, or a low concentration of pH. Either way you want to think about that. Notice that hydroxide and hydrogen are going to be inversely proportional. One goes up, the other goes down. All right, hopefully stuff that you've all heard before, maybe in like middle school or whatever. If we want to keep going with this, we could also have what's called the POH, which would just be the negative log of OH minus. And we're going to see that this one would just be the opposite of the pH scale. Where a low POH means more basic, and a high concentration of hydroxide, and a high POH is more acidic with a high concentration of H+. All right. Hopefully, so far so good. It's really just the opposite of it. Remember that they're remember, inversely proportional, so we would expect their scales to be inverse as well. So, with that in mind, if we know that this is 10 to the minus 14, if we take the log of both sides, negative log rather, we can do that. And remembering that negative log is the same thing as P, this tells us that pH plus POH will equal 14. So we can get the POH from the pH and vice versa using this constant. Again, this is at 25 degrees Celsius. I'm not going to give you things at other temperatures, but just know that this equality only holds for 25 degrees, because we know that equilibrium constants do depend on temperature. So we would expect different numbers at different temperatures. All right. So given any of these, you can calculate the other three. You only need one of these to calculate the other three of them. So you can be given any of these four and you can calculate the rest of them. I guess I should introduce what the opposite of the log is. So we're going to use kind of the following formulas. Of course, if pH is negative log H plus will be the opposite, which is the antilog formula, which would be 10 to the negative pH. Or some people say antilog negative pH. Depends on your calculator. I think most of them have 10 to the x as the button, but some calculators will have antilog. So either way, it's usually the second function or shift function and then the log button. For POH, it's the same. And then we have our equilibrium as well. Or, oops, any of these. So we've got 6 equations here where they're kind of just the opposites of each other. We can use these to calculate any of the others. So let's say we had our let's say we had an H plus concentration of 6.24 times 10 to the negative 4 molar. Let's calculate the rest of these. So we can calculate them in any order we want. Doesn't really matter. I'll just write what we're doing here. So we're finding pH, POH, and OH minus. In my opinion, I rather hate using the equilibrium constant. I like using this formula instead, and then going backwards from POH to OH minus. But you can use the equilibrium constant if you really like. That would totally work. So if we want to find the pH of this, it's just the negative log of that number. Let's go ahead and do this. Let's see. So negative log of 6.24 times 10 to the negative 4 is going to be 3.205. 3 sig figs. If we want to find POH, we can just do 14 minus pH. Which would equal 10.795. Again, this number has 3 sig figs. We can treat that 14 as an exact number for us, or we can go ahead and put 3 sig figs on it because it comes from the 1.00 times 10 to the negative 14. For right now, we can just assume it's an exact number. All right then, so if we wanted to find the OH concentration, we could do it 2 ways. We could either do the antilog of the POH. Let me just also indicate before I forget, both of these have 3 sig figs. If we do this number, let's go ahead and do it. 10 to the negative 10.795. Did I type that in wrong, of course? Okay. We get 1.60 times 10 to the negative 11. Should have units of molar. If we do it the other way, we can use our equilibrium constant. Times the OH minus. And if we solve for OH minus, we should get the same number. But let's just do it just to make sure. Divided by 6.24 times 10 to the negative 4th. And lo and behold, yes, you do get the same number. You can do it either way. I prefer using the antilog because it's just easier to type out in my calculator or Google. So either way, it'll get the same answer. So it'll work. So that's how we can use one of these to figure out the others. And so definitely you'll have some homework on that sort of thing. Alrighty, so any questions so far on any of this stuff? I would hope a lot of this is review for you guys, but maybe it's been a while since you've taken chemistry before, and acid base you don't cover in 111, so. All right, then. Keep on chugging. So, I don't want to go too far ahead, but let's talk about strong versus weak acids and bases. Just so we are very clear here, this is irrespective of concentration. Concentration is not important when we are distinguishing if an acid is strong or not. We're only looking at the nature of the acid. The chemical formula of the acid will tell us if it's strong or not. We have 6 strong acids that we typically will encounter. Those 6 are going to be 3 of the ones with halogens, perchloric acid, nitric acid, and sulfuric acid. These are going to be the 6 strong acids we have. The reason for that is because if we look at the dissociation equilibrium for them, the equilibrium constant is going to be much greater than 1 for all of these 6. And as a result, we call them strong because they're fully going to dissociate as a result. Sulfuric acid, by the way, is only strong for its first proton. We're going to see the second proton is actually weak when we look at these in more detail. All right. This, for strong acids, we're going to see that the acid concentration will equal your hydrogen concentration. Except for sulfuric acid, we'll kind of leave that one aside for right now. But for the other ones, HA, by the way, is just some generic acid. Let me just write that out. And of course, A minus would be its conjugate base. For strong acids, we're going to see that A minus is a negligible, I think that's how you spell that, base. It is an extremely weak base. So much so that it pretty much will not act as a base. It is so weak that it just can't grab a proton from something else. And so we're going to see for our strong acids, because they're so strong, we're not going to have a reverse reaction happening. Because the conjugate base is extremely weak, it's not going to go in reverse. Then as we can see, the Kc is going to be way, way bigger than 1 as a result. For weak acids, which will have Kc of less than 1, we're going to see we have an equilibrium here where your conjugate base will be a weak base. So a weak acid will end up giving you a weak base as a result, if it dissociates. And so this reaction is truly reversible, where we're going to have that weak base could react in the reverse manner. But that's not going to happen with our strong acids. If you look at strong bases, by comparison, we're going to see that the conjugate acid, HA, is a negligible acid, where it really is not going to go in reverse. So if your base is strong, we're going to see that's going to be the case. Typically, the strong bases that we see would be something like the oxide ion, hydroxide ion, or hydride ion. These are all very strong bases that will have negligible acids. If we look at what these conjugates would be, the conjugates of these would be hydroxide, water, and hydrogen gas. These are all extremely weak acids. If we look at some of our strong acids, we're going to see their conjugates are going to be the super weak ones. So the nitrate ion, chloride ion, perchlorate ion, and I guess technically we would have the bromide ion as well in there, as well as the bisulfate. These ones are going to be extremely weak bases. All right, so we often will not see these guys contributing if we were to look at them just by themselves. Like if we had a solution of iodide, we would expect it to be pretty much neutral. If we look at some of our kind of medium ones, let's have a look at some weak acids. If we take acetic acid, or how about nitrous acid or hydrofluoric acid? If we look at the bases for those, these are going to be weak bases. So they can end up having an effect on your pH. We're going to see later on when we talk about buffer systems in the next chapter that weak acids and weak bases will do some really cool stuff together. And by cool stuff, it means you're going to hate it. But I'll like it, so that's okay. That's the important part. And if we look at a few weak bases, often these will be nitrogen containing, like ammonia, or how about acetate? That's a weak base. Let's see, what other weak bases do we have around here? Oh, carbonate. We're going to see that if we make these into conjugate acids, they're going to be weak. We're going to see all of these will be weak acids. So, yeah, right. No one likes kinetics. So, yeah, basically today is mostly all just like vocab and learning kind of some trends here. And so we can talk about how these kind of work together. So your strong acids, strong bases will make negligible conjugates. Your weak acids, weak bases make the weak conjugates. So, with all that in mind, we can evaluate the strength of an acid by looking at its dissociation equilibrium. And so, if we compare a couple here, oops. For this particular reaction, we actually call this Ka for the acid dissociation equilibrium. Acid dissociation equilibrium constant. We're going to see that would be, since these would all be aqueous, we would just be evaluating the same thing for all these different acids. We're going to see this one is going to be, I don't know, 4.75 times 10 to the negative fifth, maybe, something like that, at a given temperature. If we compare to something like the bisulfate ion, sorry, not 2 minus, just 1 minus, it's Ka. Might be something like, I don't know, I'm making the numbers up, but it's somewhere around the 10 to the negative 2, 1. If we compare their Kas, a larger Ka means more H plus, right? Because for all of these Ka, these acid dissociation equilibria, H plus is in the product side, right? That's going to be on the top of your fraction. So the bigger your the value is, the bigger that H plus is going to be. And as a result, that means a stronger acid. So your bigger Ka will mean that you have a stronger acid. A small Ka means you're a weaker acid. So if you're just comparing two weak acids together, you can see which one is going to be stronger by looking at their Kas. Sometimes we also use pKa, which would be the negative log of Ka. Would be the opposite, where small pKa is a stronger acid. Just because, again, these Kas can have pretty small numbers. Here, let's go ahead and look at some weak acid Ka values. Let's look at a nice table here. Aha! Big old table. Yeah. Let's do this. Will this work? Yeah. Okay. Let's zoom in a little bit here. Okay, apparently I can't zoom in. Well, let's go here then. Oh dear. Aha! Oh my gosh. Okay, now we can kind of see them. So here's a bunch of acids, their conjugates, their Ka values, and their pKa values. This table is organized such that the strongest acid is on the top and you get weaker as you go down. As you can see, the pKa values go up, the Ka values go down. And so you can see, of course, those are inversely related. But we can compare a particular acid by looking at its Ka value. So if we were to compare acetic acid versus benzoic acid, these two, we would look at their Ka values and say, aha, oh look, benzoic acid has a Ka that is bigger than acetic acid, or acetic acid's pKa is bigger than benzoic, and the smaller one is going to be the winner. So we're going to see that in acid-base reactions, the stronger acid is going to be the one that wins out over a weaker one. And so if we're kind of looking at, what's going to react with what, the stronger acid is going to react with the stronger base in any given reaction. So we'll look at this more next time. So we'll just kind of, here's some numbers for you guys, but in no way are you required to memorize these at all. It's totally not important for us to do that. Okay. So, we've done quite a bit today. Quite a bit. We're going to look at how to figure out the H+ concentration for a weak acid next time. And we'll talk about bases some more, and we'll get to some more stuff about salts as well. So with that, our kind of intro to acids is done. Tomorrow, if anybody wants, throw it in Discord. If you want me to do an exam review tomorrow, we can do that. Otherwise, just look at the key and try and go through it yourself. Maybe worthwhile to work through the problems to make sure you can get it after looking at the key. So, with that, maybe I'll see you tomorrow. Maybe I'll see you next week. Oh, excuse me. All right. Enjoy your weekends.